let's say hi to our speakers for today. And if you haven't joined these sessions previously, this is probably the fourth or the fifth session that we've done that is specifically about LLMs. So we do suggest that you go and check out the YouTube channel. You'll see there are a lot of content that we've done previously, and a lot of the things that we're going to be talking about today will lean into that a little bit. And this is really, sharing our experiences at both Blattner Tech and at Superwise in what we've seen over the course of building out services and products around machine learning and around LLM specifically. You'll see a little bit of what we're doing also later on during the session today. So we have three speakers with us today. David is going to be kicking us off. So he'll shortly take you through what we're going to be talking about today. And then Andrew will take us a little bit deeper into some of the topics, and Owen will be closing out for us and giving us a little bit of taste on the infrastructure side versus the architectural side. So with that, I'm going to hand this over to David. David will take you straight into everything.
Sweet. Thanks so much, Moran, and thank you so much, everybody, for joining another session with us. I want to take us through a brief review of prompt engineering, where we were and where we're headed. Andrew will take us through some evaluation frameworks in the area of monitoring and observability. That certainly lies at the core of a lot of what we do here at Superwise and Blattner Tech as well. RLHF is really a hot button topic these days when it comes to incorporating the interactions and interfacing with diverse audiences into how LLM solutions perform. And then, as mentioned, we'll get into some architectural and infrastructural considerations for how we can continuously improve a lot of these solutions. But before doing all of that, I think it's just worth noting that at its core, generative AI is another perspective vehicle for creating compelling data-driven stories in whatever communication medium meets the needs of their audience, right? So while in past webinars, we've covered how we can move from a monolithic pre-trained model, something like a private LLM deployment, to more of a modular solution, what you might call the best draft of your task-specific story through fine-tuning, and the telling of your story, which I think is a different, fundamentally ongoing, and ultimately continuously improving initiative. So how we deliver to our audience, how we respond to their feedback effectively and efficiently, that all falls under LLM optimization. And it's important to make this distinction as we leverage, say, a prompt optimization framework that's automated, or an evaluation and monitoring approach, maybe some optimizations in infrastructure. All of these best practices that we'll cover today will allow us to move from performant LLMs in a testing environment to more production-grade solutions that developers can continuously improve. So with that being said, I want to start with some review from prompt engineering and how we lead that into more established frameworks, primarily in the area of prompt engineering optimization, right? It's really no secret by now that hallucinations abound in LLM solutions left unchecked, and one could argue left non-optimized. Right, much of the root cause behind this so-called ego problem of LLMs harkens back to symptoms of both model overfitting and underfitting. Right, by that I mean underfitting occurs when the model fails to capture user-specific language. Maybe there's specific domain knowledge, any industry-specific information that extends beyond the public sphere. This can lead to inadequate performances in tasks that do harness that specialized language. On the other hand, model overfitting happens quite a bit as well. LLMs are trained on massive stores of digital content, and echo chambers abound in the public sphere, on the web, all over the place. In reality, there really is a green path here, and there's a lot of misconceptions around the misinformation and disinformation, inviting criticisms of LLM-based solutions not somehow being productized or production grade. We will cover how to get over some of that misinformation and disinformation today in some consistent optimization practices around input quality, output evaluations, and ideal architectures. So with that being said, let's get started. Just as a point of review from our prompt engineering webinar, especially when we work with the computational veil of a black box, it is helpful to have somewhat of an opt-out. It's crucial for us to shine some light on the LLM's overall confidence, which certainly can vary due to things like use case fits, lack of sufficient context, or maybe some unclear instructions, right? A simple I don't know for non-confident answers may allow for components of the request that your LLM is uncertain about to be passed to, say, a generalized LLM like ChatGPT, the World Wide Web, or human support, whatever you deem is more important. And user frustration in this way is effectively minimized as a unilateral LLM infrastructure becomes somehow expanded through opt-out avenues. Self-consistency is just another way to handle that architecture, right? Self-consistency as a point of review is used to mitigate some inconsistencies by running the same prompt more than once with a non-zero temperature, collecting the results, and choosing the right path for defining the type of merging strategy. For categories, right, this can be done through majority vote, majority rule. For something more computationally, we can do an average, right? In this example, and in a lot of similar examples in which logical reasoning for problems where the chain of thought is not too big, it works really, really well, right? The LLM here reasoned that Nashville and Atlanta are in the same time zone at one point, which is a hallucination here in the United States. But by and large, given the simple logical steps that are required to get to the answer of 11 a.m., the simple majority rule leads us to the right answer on its own, right? But for use cases in which quantitative accuracy is more critical, applying a type of confidence threshold based on proportion breakdowns can either refine your reasoning paths or redirect users to more helpful resources, as mentioned before. And as you see in this example, right, we have a uniqueness threshold of 50%, which would send the user the correct time to show up to the airport for an upcoming flight. This level of tolerance around uniqueness or the overall uniqueness of the response can certainly expand and contract according to the complexity of your chain of thought being used and the degree of accuracy being promised by your solution. Now, once these logically sound and accurate chains of thought are identified, either by the uniqueness of the overall probability of the generated output, as I mentioned, a set of new training shots could certainly be passed into the overall prompt in a type of more semi-automated pipeline, right? So this idea of active prompting gets at that idea. It involves the least certain edge cases being intercepted and then corrected through human-in-the-loop prompt engineering in order to bring more use cases in scope. As Andrew mentioned later, prompts should really serve as a dynamic resource rather than static givens. And this process is far from a one-time fix it and forget it cure-all, right? We need to iteratively improve as the context of the LLM changes, as new models and frameworks get introduced and considered, and certainly as diverse audiences begin to interface with these LLM solutions with their own natural language, their own vernacular, et cetera. That's where test-driven development really comes into the mix. Prompt engineering within this TDD framework is really critical to ensuring that your prompts stay relevant, that their outputs stay accessible. The underlying calculations are both explainable and interpretable to a diverse audience. So explainability, accessibility, and interpretability all kind of lean into each other here. Interpretability, you can think of as high-level observability, things like feature importance, whereas explainability is more model level or cohort level explanation of how an LLM actually makes decisions. So given that productized LLMs are still somewhat in their infancy, TDD is far from standard practice in generative AI, but it has been widely embraced in more traditional software engineering disciplines due to its promise in how we can accelerate development, reduce errors, and ultimately instill continuous improvement. So at a high level, developers using this TDD framework start by writing test cases for desired functionality and then start to work backwards. They write the minimum solution necessary for these tasks to pass through. Code factoring occurs iteratively as new tests are introduced into the system. But our definition of done when it comes to LLMs, our constraint for success with LLMs, can be somewhat ambiguous at times. A lot of us are familiar with this. It makes prompt quality assurance somewhat subjective by nature. And fortunately, with TDD being an AI augmented framework, right, we can move from something more modular and grant some more fine-tuned solutions more quickly, more narrow, more domain specific, right? I'll cover how we optimize our LLM output in just a few moments. Andrew will cover the training and evals, but for now, it's important to remember that under this framework, developers need to be comfortable with failing often and failing quickly. Ideally, you'll want to introduce a combination of hard and diverse test cases to challenge your LLM. Easy or repetitive examples aren't really useful here because it's difficult to observe improvements when the model already succeeds. With that being said, implementing sufficiently challenging edge cases at scale is far easier said than done for a variety of different reasons. Beginning with model hypersensitivity, just minor token variances can sometimes create some major output deviations. We see that in this silly poem generation example, where even with solutions that are in fact a zero temperature, little variations in the inputs embeddings can cause some major output inconsistencies that make distinguishing variance in the output for just messy noise pretty tall order, right? Proliferated interaction styles, especially when diverse users or domain-intensive use cases are introduced, things like slang, abbreviation, shorthand, domain vernacular, all that should be incorporated into the LLM to account for more user-friendly interfacing. That's somewhat of an extensive task as well. Exhaustive error handling, right? Especially when making solutions more bespoke, the changes made during test-driven development become very data source specific because the edge cases are very data source specific. And because of this more exhaustive and representative shot training, it's not very directly translatable to other applications. Surely using best practices can make these modular features a lot more seamless, but there are always going to be gaps to fill, right? And finally, with additional context comes potential noise that you're introducing to more healthy cases. That's just an intuitive risk that you have to take when more tokens are assigned to edge cases in general. So what can we do here? How can we move from this proven, tried and true development cycle to more efficient operations at scale? One possible solution harkens to a lot of the reasons that GPT towers above the other big players for most generative tasks, namely in the area of what's known as reflection, right? GPT-4, it enables additional AI to analyze its mistakes, improve performance in real time through this self-contained loop. So this loop incorporates reinforcement learning through human feedback, as we'll account for in just a few moments, and it also instructs the model itself in how it resolves decisions and builds out new strategies, right? Now, the trigger for an LLM like GPT-4 or its alternatives in order to revisit original LLM output can either come from explicit feedback, the thumbs down, thumbs up functionality, or through a separate evaluation cycle that assesses whether this output really achieves the requested format and includes the right content. For example, right, we'll take this airport operations chatbot. For applications like this that only evaluate general positive or negative feedback on outputs, it's often best to encourage the LLM to make the request more relevant, specific, and helpful. So these three areas are direct enough to encourage the LLM to make changes, but still generic enough for creative self-assessments of what actually went wrong. For applications with more granular negative user feedback, though, such as the airline customer saying that this output is very sparse, maybe it needs more info on a particular delayed flight, this label of incomplete or untrue could be directly applied to a prompt template geared toward correcting that specific error, right? So this process could, in theory, be repeated until a user is satisfied, but it's important to keep general user frustration in mind. And much like with self-consistency, a lack of front-end visibility may lead to more happier customers, so long as the LLM can evaluate its own generated content by itself in a closed loop, right? So before delivering this response to the front end, for example, the LLM could refine its own output until a desired level of completeness or relevance or truthfulness or a blend of these quality labels, all against an assigned threshold that you'd like to use as a type of sanity check on the initial output, right? So maybe the root cause of your edge cases can be handled in this way. Maybe the root cause can be attributed to the persona or the listed output requirements in the prompt itself. And to that end, we can apply really similar techniques to prompts themselves through what we like to call suitability scoring. So suitability scoring is a really streamlined implementation of test-driven development, with LLMs taking center stage and handling a lot of this menial cognitive work associated with manual prompt engineering. Namely, how do we frame the prompt to reflect the desired task? How do we iteratively generate prompt alternatives based on what we know to be the leading candidates, all of which are introduced, by the way, as context to this overall meta prompt. It's really just the optimization LLM. And finally, how do we evaluate new lists of diverse prompt options based on some type of suitability metric, right? So here you can think of the suitability LLM as a classifier that assumes the role and persona of a prompt engineer. If there is some type of human in the loop interactions with respect to what to exclude, how to format it moving forward, that can be implemented at each loop as well over time. That implementation may reduce the likelihood of hallucinations and rabbit holes as well. But during the process, it's really critical to develop a working definition of done, all the while being mindful of your token limits, maybe cleansing the prompts of any redundancies in there, and considering the additional costs that may come with each additional self-assessment loop, right? Hyperparameters are a big piece of this as well. Randomness controls like temperature, top K, and top P should be fresh and top of mind. For prompt generation, given that it's not a very deterministic task, right? Maybe a moderate top K level, maybe a moderate temperature will help you balance creativity and coherence pretty nicely here, right? As a really quick point of review for us as well, the limited scope of a single prompt may invite questions around where do we turn when the roadmap to our definition of done is not particularly clear? Maybe the LLM framework can't afford to have the same input, operation, and output workflow time and again. What if we need the LLM to reason across, say, a toolkit of different actions and decide on the next best step? That's where a lot of these agent-based or agent-enhanced approaches can come in, right? For example, a user asking for a summary of the 7-day weather forecast for the departure and arrival destinations of an upcoming flight may encourage an agent to generate and execute 2 different weather API calls and an overall LLM general summary, right? So as we move from reasoning to action, it's really contingent on a stable integration of multiple capabilities to achieve this common goal. That enables some growth here. So how can we implement and strengthen the performance of out-of-the-box agent tools in some of our broader architectures, for example? So let's consider a really simple example that deconstructs at a high level, a custom alternative to the new OpenAI Assistance Code Interpreter tool, which is really slick on its own, by the way. But in complex cases extending beyond, say, a simple data aggregation in pandas, an architecture that gives us some entry points of transparency here can help us protect against actually executing code that's not complete, not accurate, or worse yet, not satisfying the actual requested task running on your data. So here you'd want to provide in detail a description of your task that you want to achieve, maybe provide some metadata if you're using structured data, for example, column names and their corresponding types, and any other guided examples for how you'd like the code to be formatted. As this code is generated, sanity checks on whether the proposed request actually satisfies the original user request. That can help limit hallucinations, and a debugger LLM working in the backend can actually satisfy a lot of these error resolutions through prior code blocks that succeeded, as well as some of the error points, modifying the nuances and so on. So as a really quick overview, that's LLM prompt optimization and output modifications. We'll pick up where we left off in a moment, but I'll pass it off to Andrew now.
Thanks, David. Moran, are you going to hand over the controls?
David needs to do that from his side.
All right. Well, while we are waiting on that, okay, cool, got it. Thank you. So thanks for that overview, David. So now we're going to get into the evaluation portion, where we talk about LLM alignment, how to determine when your LLM is aligned, and how to monitor in the loop. So first off, what is the LLM alignment problem? So whenever we have these large models, it's impossible to predict the exact output from any given prompt input, right? And in applying these LLMs to a lot of business cases, that creates an issue because we want LLMs to be customer facing or internal facing. We want them to be honest to us. We want them to align with our business values, right? Um, and with traditional methods, it's pretty difficult to do that with just straight learning because LLMs often don't learn what we try to make them learn. They often learn unintended things. And so the alignment problem is to try to make the LLM aligned to our business values. So here in this graphic, there are two values here. There's the helpfulness value and the politeness value. You can see there are four quadrants here. One quadrant, the upper right quadrant, is the only aligned quadrant because it is both polite and helpful. The other three quadrants are what we don't want to see. These are misaligned. So whenever you ask something, for example, about smoking safety, you can see here a good alignment will say something about, don't light fires near explosive materials, but something that is not polite or helpful will, not even answer our prompt. Um, Let's see. Oh, there we go. All right, so here are some more misalignment examples. So there are many, many types of misalignments, but here are two common ones. So a factual hallucination is simply whenever we get, or the LLM tells us something that isn't true. So in a lot of use cases, you'll want honesty back if you're having something, especially Q&A focused, customer based. You'll want it to be useful in that sense. So whenever we ask about the first person to land on the moon, clearly that's Neil Armstrong, but a misaligned LLM may tell us it's Yuri Gagarin. Or another misalignment type is instructional inconsistency. Wherever we tell it to do something, tell the LLM we want it to do something, and it does something different, right? So in this example, we want a translation of a sentence from English to Spanish. Instead, it tells us about the capital of France. And so in applications where you want to instruct LLM, misalignment can cause quite a few business issues. Um, so there are generally three approaches that we're going to at least discuss in this presentation for how to get around this alignment problem. So what I'm going to talk about here is the LLM evaluation approach. So the value-based training where we try to get your underlying LLM to be aligned with your business values. And then David is going to talk about retrieval augmented generation and some guardrails and demonstrate how the supervised platform integrates those. So with LLM evaluation, there are 5 steps, and we're going to go through each one. So the first step is to identify your evaluation goals. So whenever you're trying to align an LLM with your values, you first have to determine what values those are, right? A good rule of thumb for these is they should be one word for each value, right? You want them stupid simple. You want them to be very easily definable common words, just so you know when you get it and you're not overcomplicating things. So examples of this are succinct, trustworthy, relevant, and polite, right? These values vary a lot by your use case. So for example, if you want a summarization LLM, you'll want it to be succinct, and you'll want it to be relevant, right? You'll want everything in the original text to be included in a shorter blurb, and you don't want to miss anything, right? So you want the information all to be there. It is important also to limit the number of values that you pick, just because in the alignment process, whenever you evaluate, if you choose too many, it can be difficult to get a really good alignment on any one in particular, and so you kind of get a mediocre result. So it's important to pick maybe 2, 3 key values to align based on. Um, so now the second step, once you have your values, you want metrics, right? You want some numbers to be able to assign to each of these values to measure them. So this is split into 2 different categories of metrics. You have your objective metrics, which are the ones we traditionally think about when we think about metrics. These are things that are directly computable or checkable. Something that you can reference. For example, if you have an LLM that you want to tell you your flight status, right? Whether it's delayed, on time, or in flight, right? You want, or you, an objective metric is able to take that flight status and directly compare it to a table, right? So if the LLM tells you that a flight is delayed, you can directly check, is that flight actually delayed, right? Whereas subjective metrics are more opinion-based or by consensus, right? These are the things that are more intuitive. As humans, we understand it. You know it when you see it, right? So these kinds of things are more about writing quality, meaningfulness, relevance, things that are harder to peg down specifically to a true or not, right? Um, so whenever it comes to the subjective metrics, the more traditional approaches don't work as well. So you have to use a evaluation LLM, which we'll talk about in the following slides. But as a good rule of thumb, your metrics should be quantitative, reliable, and accurate. And they're very important because good metrics and accurate values equal good alignment. Um, so now getting into how you will build an evaluation LLM. So if you're using subjective metrics, a good first step is to build something called a golden data set. Now, this golden data set is extremely important. It can make or break your evaluation. And you will want to compile a data set over your intended use cases, right? So every single type of thing you expect your LLM to see, and only those things that you expect your LLM to see, is what you're going to build this data set from, right? So you'll want between 50 to 100 examples typically for fine tuning. If you want to do fine tuning for your evaluation LLM, you'll want more than 100 examples, but 50 to 100 is typically a good starting place, and then we'll get into building a synthetic data set later for fine tuning. If you're using zero-shot evaluation, you won't want to, or you won't need this golden data set. That does have some applications, but in general, zero-shot evaluations are pretty limited use cases just because they don't give you as good of an alignment. So production data is very important, but it's also typically very limited. It's really nice if you can have it, but you don't always have it to start with, and you can't really trust to build your alignment based on it. So we're going to talk about how to generate synthetic data shortly. But first off, we're going to talk about developing evaluation models. So there are a lot of good models that are pre-built to do evaluation on LLM alignment. So my suggestion is before you build your own model, before you customize your own LLM specifically for evaluation, you should test out the pre-existing models like ChatGPT, or maybe even these more customized models like Prometheus GPT Score, just to see if they work, right? Because for lighter use cases, for cases where it's maybe like a customer service bot, where it's not life or death, it's not a medical setting, um, they do a decent starting point, or for maybe like a demo. Um, but for building a more customized LLM, you'll first want to create an evaluation prompt. So evaluation prompts are one of the key things you can tweak in your evaluation method, you want them to correspond to your value. So if you have a relevance value, you're going to ask if, the context is relevant when evaluating your LLM. So when you have an LLM output from your evaluatee LLM, you're going to use an evaluator LLM with a prompt that is based on your context. So then the architecture generally looks like you have your evaluatee LLM right here, and you have any types of context that comes along with that. You're going to classify with your evaluator LLM a classification for based on your prompts. A classification based on your value in a relevance example is the context relevant or not, right? So you're going to give a context, is it relevant? You're going to give a class, is it relevant or is it not relevant? So once you build these two classifications, you can score them, how many are relevant, how many are not relevant. A passing metric is if it's above a certain threshold that you can decide. That's a knob you can play around with. Um, and you can also include some reasoning there. So next, a note on different ways to customize your LLMs. So we talked about zero shot, but there's a big difference between few shot and fine tuning for your LLM evaluation tools. So both of them use your golden data set, but fine tuning is usually a lot more intensive on your data set and intensive computationally. It's a lot more complex to build out. So you really only want to use fine tuning in those more heavier use cases. So whenever you want to have a more integrated approach with reinforcement learning with human feedback, that's when you may want to use fine tuning because it's easier to put in that loop. But in my experience, few shot learning on your golden data set initially is a really good first step for building a competent evaluation model. So next is to deploy and iterate. So this specifically for evaluation, it shares a lot of commonalities with test-driven development. So a good rule of thumb here is to think of evaluation as a continuous process, right? So whenever you evaluate, it's not done only whenever you finish building your operating LLM, your evaluatee LLM, right? You want to evaluate continuously whenever you change your business values, right? Whenever your goals as a business may change, you need to reevaluate whenever you retrain your model, whenever just periodically you'll need to reevaluate based on your use case fit, right? Um, so it typically takes several iterations for your evaluation to properly align. This is a pretty growing field. It's not very well understood or well documented quite yet how exactly to get an LLM to give good alignment. So it's more of a tools of the trade as of currently, but here are some tips to get good alignment. So we talked about this in the last webinar, but specifically for LLM evaluation, you'll want your prompts to be clear and specific. If your prompt is vague, your model doesn't really generate good classifications. Um, and so it's good to have clear prompts. You'll want to experiment with different phrasing. So use a lot of synonyms for your values. If your value is honest, you might say truthful or something like that. Um, Change up the wording a bit. It can go quite far with your evaluation practicality. You'll want to use instructions. So you'll want to tell your LLM to classify, right? Say, generate me classes based on relevance or something along those lines. And that will help to increase your output there. Adjusting max temperature or adjusting your temperature and your maximum tokens. This is another knob to twist to try to get your alignment more spot on. So now into a few methods of synthetic data generation. The first method we're going to talk about is retrieval automated generation. So this is where you want to augment your LLM with a third-party data source. So a ground truth data source. There are two ways to do it. You can do a fully automated way with two LLMs. You'll get your first LLM that will generate or that will pair up relevant documents with your user requests. And you'll get a second LLM that will judge how well that first LLM performed, right? So there's this loop there that can generate better results, or you can do a manual few shot approach with just one LLM. You can do few shot training by building a shot set. So some important notes about building a shot set. You'll want to make sure that each shot that you build has a diverse sampling from your data set. You'll want to make sure that each type of thing that you want your LLM to do is represented in each of your shots. So now talking about generative adversarial networks or GANs. So this is another, I would say it's an older approach, but old is still good in this sense to generate synthetic data. So this method uses both a generator and a discriminator in adversarial training. So the generator model will create your samples, and the discriminator's job is to try to discern between real data and synthetic data, right? So you'll have a subset of real data and your generated data, and through adversarial training, you can make the generator better at making fake data. Here are some other synthetic data approaches. There are many synthetic data approaches. These are kind of the main ones beside GAN and RAG. But that covers synthetic data. So now I'm going to hand it back to David to talk about reinforcement learning with human feedback. All right.
Yeah, thanks so much, Andrew. And want to just take a few moments to talk about some productization considerations, moving from test-driven or test environment POCs into something more product-ready, right? A lot of these LLM optimization considerations are relevant in this case. We'll get into those in just a few moments. First, I want to start with concept mappings, which effectively is just a provision of additional context to the LLM, which with respect to what you anticipate your users to implement in terms of a natural language request, abbreviation, shorthand, vernacular, and how that information is actually stored in your data. So in the case of structured data and doing a type of question answering on top of a structured database, you may want the actual row values to be mapped to actually how the conversation is happening on the user side, right? It can be a way to preserve tokens and be a concise shot alternative. As we know, composing a high-level mapping like this is often much easier and much faster than building out a full-blown shot, right? Table descriptions pick up where that left off as well, right? What each table contains beyond column names and data types to better instruct the LLM on where to find information, right? This helps the LLM zoom in on the most relevant data, wherever it lives, however it lives. It provides some scoping for that application that way, right? And finally, we have this idea of user-level RLHF. Now, it's important to remember that in both of these frameworks, the feedback aggregation level to be used can certainly vary, right? You can have it be per conversation thread, per user group, or ultimately per an entire tenant or enterprise level RLHF, right? For example, you may want to implement group level implicit feedback in order to produce more succinct but contextually rich summaries for C-level executives, and maybe some more robust or in-depth explanations for mid-level associates, right? Other demographic differences like the location of an office or your department come to mind here as well. Alongside a lot of these considerations comes the question of how specific you'd like the human feedback itself to be. Perhaps a simple thumbs up or thumbs down may suffice, but most RLHF drill down evaluations are not particularly straightforward without some additional labels on completeness or truthfulness, etc., as we have mentioned. The number of these options that you provide really depends on the level of buy-in on the user side to this feedback cycle, as well as the level of analysis that you're hoping to achieve. We can take a look at a really quick example of how this works at the production level on our supervised platform, which effectively is an end-to-end platform for deploying, testing, training, ultimately monitoring and observing LLM applications, right? We have an enterprise-grade user management system at the tenant level in which users can modify permissions, add security preferences, and leverage our robust API stack driving this end-to-end process flow, right? We also enable direct and secure connections to data sources, both structured and unstructured, which can serve as the foundational tool and the foundational context for any of your LLM applications. In this case, we're picking up with the airport customer service or operation retrieval application. It's worth noting we have a slew of different options across closed source as well as private deployments of your own LLM. All of these capabilities, regardless of when they were trained, work all the same. We can host it where your infrastructure lives or on our own, certainly on-prem as well. But taking this concrete example of airports and flights by the number of aircrafts, right, we may have data that's particularly near complete, but there may be some flights or maybe some aircraft types that are missing in this case. We not only provide the thumbs down RLHF, but provide a lot of different customizable and configurable labels for why that answer was in fact poor quality, right? So this gets sent and monitored at the tenant level. We can then do some feedback analysis directly included in a Jupyter notebook provided to all supervised users in just a few simple chunks of code. We can do a lot of this drill down analysis into when a request was made, what the input was, the output was, and why it was good or bad quality, right? Taking this one step further, we can leverage a lot of this out of the box data in a visualization environment. I'm moving beyond the supervised platform and using Grafana here to showcase how a lot of these visualizations can track the most positive phrases, most negative phrases, and a lot of health and sanity checks as these requests develop per application over time. What's really critical to note here is our out-of-the-box meta features and NLP, like sentiment, toxicity, text complexity, and word count, a whole environment and a whole family of out-of-the-box meta features in our open source LLM tool. So any LLM application that you leverage and imply human feedback can be AI enriched with this LLM tool as well. So hopefully you found that helpful. I will go back to our slides here. Now, up to this point, we've focused largely on how to cater LLM solutions to our audiences, but in terms of maintaining consistent response quality across a wide variety of user requests, that is really only a small piece of the puzzle. We also need to ensure that our LLM system faithfully and truthfully and really succinctly adheres to our knowledge bases when generating output, right? That principle is just the core tenet of any production grade solution. And in theory, a reg system offers a really solid blueprint for that kind of context-driven question answering. As a quick point of review, a simple reg system contains three primary layers, if you will. There's this content layer involving the selected corpus of documents, splitting it into smaller chunks, indexing them as embeddings, and ultimately vectorizing them in a vector database. There's this retrieval layer, which involves a lot of the semantic similarity familiar to autoencoders like sentence transformers. And then finally, this response layer, which involves contents of relevant document chunks being passed to the LLM to create the answer. But as we know, in this day and age, production grade RAG has become somewhat of an oxymoron in most circles, and that's largely attributable to a mismatch between the default RAG configurations and the nuances in your supplied documents. For example, default similarity search with BERT and its alternatives has shown a lot of sensitivity to plural versus singular and positive versus negative, as you see in this pretty funny real-world example. You often need some pretty extensive hyperparameter fine-tuning in order to ensure that one chunk is mapped to one idea and one idea only, and that a document chunk is passed in a dense way to the LLM for exhaustive search, right? There's really no standard top K or the top number of documents to apply across the board, and there isn't a very easy measure of correctness here. In addition, requests that mimic something as simple as a control F search on your digital documents, those don't need really any additional parsing, but more complex requests involving comparisons between content, maybe comparison across multiple chunks or multiple big ideas, that may invite far more complex architectures and far more complex techniques. Right. Finally, especially for documents with really contextually significant formatting in their headers and subheaders, bulleted lists, etc., the chunking to embedding this similarity search process is just a lossy by default. So the big question becomes, how can we boost this performance without sacrificing any elements of the overall UX? And perhaps the easiest answer and the lowest hanging fruit for anything beyond our out-of-the-box defaults lies in the area of how we chunk our documents. Right, so take the Oxford English Dictionary, for example. You have each word and corresponding definition, assuming a consistent structure across the board. Divisions by the formatting conventions could ensure that definitions, regardless of their length, could not be split into multiple chunks. They only get one chunk and one chunk only. So syntactical rules like splitting on titles, bulleted lists, etc. here give some semantic similarity when these kinds of clear syntactical conventions are present. And more likely than not, a given word and corresponding definition may represent an entirely different context than its neighboring entries. However, as we know, with the dictionary, words can have a set of very different definitions in what we like to call polysemy. And perhaps more importantly, the definitions of a word's synonyms in remote chunks could be really helpful in your understanding of the big idea that the word actually represents. So perhaps an even more dynamic alternative for chunking may be relevant, in this case, semantic chunking. So building out semantically close-knit chunks could ensure minimal loss. This is especially true for question answering applications that require a high number of documents being passed to the LLM. To that end, semantic chunking may be an even more accurate way to both filter and segment document chunks, even for the most structured knowledge bases that you may have, right? So semantic chunking assumes this three-step process for regrouping ideas expressed in your documents without needing to reorder the sentences as they were initially written. So that's a pretty powerful feature as well. It may invite some built-in contextual compression methods, but there really is a drawback here that is helpful to be mindful of. Even with the reordering of sentences, the regrouping of sentences in new ways, that can still diminish the context and the original structure of the original knowledge base. We can circumvent some of those issues by just a little bit of extra labeled data. This is where self-querying retrieval comes into play as an option. After all, a general rule of RAG requests is to give them as much structure as possible. So an LLM extractor deployed on top of a traditional RAG system, for example, can iterate through a set of defined metadata fields and parse out both the structured component and the unstructured component. The unstructured component being what we're familiar with, pertaining to the actual content of your corpus. So this approach, I guess, presupposes that anticipating user requests, the types of structured fields they might be interested in, is possible. And in many cases, it certainly could be, so long as developers have a solid understanding of the knowledge base and that accurate metadata reduces the amount of noisy chunks actually passed to the LLM in the end. But goes without saying, with large quantities of documents, data labeling is not a very easy lift. And customer-based solutions, customer-facing solutions on websites and product catalogs could invite a lot of time. Even the most robust web scraping or OCR solutions could require some pretty extensive undertakings here. So perhaps as opposed to supplying data, you'd prefer to enhance the structure of your reg system by making sure that the entirety of a big idea in question being referenced is actually being passed to the LLM as a whole, right? So parent documents can come in the form of original documents, provided that they're sufficiently small, or you can provide them as a set of smaller chunks, right? So unstructured or semantic chunking becomes extremely helpful here. In this case, the high-level concepts and the specific details being stored in a RAG system together. So really the big idea of the request is the focus here, but prioritizing that often may come at a cost of including more potential noise or excluding child documents that are remotely located, either just by being in the wrong place by accident or just not being intuitively related to what is in fact the right answer, right? And I'll conclude with this, as with the famous garbage in, garbage out principle, even when using the most relevant chunks within your vector database, if some information in your corpus is incorrect or outdated, the output will always be bad, right? Implementing something like chain of verification can help with this. It can help defend against faulty logic as a way of gaslighting the LLM, for example. That's a more complex system, but dividing and decomposing a query into smaller subqueries is a pretty easy undertaking on its own, right? So processing each request one by one can minimize the likelihood that bad output is just due to these semantic differences, right? And this query decomposition can really lend itself to outsourcing particular subrequests to, say, the World Wide Web, in the event that a part of the request needs some more external context, right? So with Joe Biden's presidency coming to a close here in the United States, if I wanted to ask whether or not ChatGPT has been made available, we may need to search the web for when ChatGPT was launched in the event that that exceeds whatever the training cutoff of your LLM was. So with that being said, I will pass it off to Oren for some closing remarks on infrastructure.
Thank you, David and Andy. So I really want to focus in the next 5 to 10 minutes about some, sorry about that, about some infrastructure consideration. I think so far we were really mostly focused around the algorithmic options or the process and methodology methods to fine-tune. But now I want to shift a bit to talk about infrastructure consideration. Now, when talking about infrastructure, we could discuss in very high level about, generally speaking, two main use cases. One use case is when we are using a third-party vendor like OpenAI, Google Gemini, or any other third-party vendor, versus talking about when we need to deploy our own LLM, whether it's based on something we really built from scratch or whether it's something we started with an open source and fine-tuned. Now, between the two options, of course, the second one is much more complex from infrastructure perspective, because when we are using a third-party provider endpoint, so actually most of the infrastructure consideration or challenges are already solved for us. Maybe we should still focus about how to reduce cost with some caching mechanism. We'll talk about it later on, or sometimes even with the third-party providers, the latency is not good enough and we need to optimize that. But beside of that, I think most of the infrastructure, I think by definition, is in the third-party provider stack, and you shouldn't deal with it. But whenever you do host your own private LLM, and there's many reasons of why you should do that in some cases, not every time and not for everybody, but in cases that you really cannot share data outside externally, or you don't want to use a third-party vendor, you really need to be expert in those infrastructure considerations. So let's review some of the main highlight points that you should consider when deploying such LLM. So the first one, let's talk about quantization. I think model quantization is one of the most interesting parts and infrastructure consideration you could take. It really involved the mapping between the infinite range of model weights, that could have infinite number of sets, to a finite number of sets. It usually being done by converting them from a float representation to a 8-bit integers instead of 32-bit floating point representation, or sometimes even there's a lot of papers talking about even reducing it to 4-bit or even less. So talking about quantization, there are primary two types of model quantization. First one, post-training quantization, or by its initials PTQ. This method involves converting the weights of a pre-trained model to a lower precision, but without doing any kind of retraining. While PTQ is simple to implement, it may marginally reduce model performance because of its loss of precision in weights values. PTQ can be applied to both closed source models like GPT-4 and existing private LLMs. And despite the potential of slight aggregation inaccuracy, PTQ does offer appealing benefits such as reduced memory consumption, faster inference times, and improved energy efficiency. Now, the second method is quantization-aware training, or QAT. In contrast to PTQ, QAT incorporates the weights conversions process during the training phase. It's part of the actual training phase. Now, this often leads to a superior model performance, but it's, of course, computationally more intensive. Now, a widely used QAT technique is quantization-aware training with linear range adjustment, or by its initials, QLoRa. This approach is suitable for private LLMs during training, and by integrating quantization-related operations like scaling, clipping, and rounding into the training process, QAT optimizes model weights to mitigate accuracy loss associated with quantization. Notably, QAT eliminates the need for separate calibration after training, as calibration occurred during training, making the model quantization aware and preserving accuracy during real-world inference. Now, considering the trade-off between precision reduction and model accuracy, the choice between a smaller full precision model or a larger quantized model with comparable inference cost depends on various factors. But eventually, researchers have shown that in some scenarios, quantized models not only demonstrate superior performance, but also offer reduced latency and enhanced throughput compared to their full precision counterparts. So when comparing models with similar inference costs, large quantized models can outperform smaller non-quantized models, and this disadvantage is particularly pronounced with larger networks as they experience less quality loss when quantized. So that's about quantization. Let's talk about pruning. So pruning is not specifically just for LLM. Pruning is a concept from general purpose machine learning models. In general, in machine learning model, pruning is a technique used to reduce the size and complexity of a trained model by eliminating unnecessary, could be parameters, connections, features, number of layers in a deep learning model. Pruning aims to improve the efficiency and the inference speed of the model while still maintaining or even sometimes even improving the generalization and therefore its predictive performance. Now, this process involves identifying and removing redundant or less important components that, as I've said, might even lead sometimes to overfitting. Now, that's often guided by criteria such as weights magnitude, sensitivity analysis, or iterate optimization methods. Such pruning can be applied to various types of models. As I said, it could be for LLMs, but also for traditional ML. Now, let's talk about more specific pruning techniques for LLMs. I will talk about two main methods. One is structured pruning. In this method, it involves removing entire structural components such as neurons, channels, or even specific layers from the model. Structure pruning results in significant reduction in the model size while still preserving the overall LLM structure and architecture. Unlike unstructured pruning, structured pruning does offer more control and it's more scalable for larger models. In unstructured pruning is a straightforward technique that targets individual weights or neurons by applying a threshold or zeroing out parameters below a specific threshold. Unlike structured pruning, unstructured pruning does not consider the overall LLM structure and leads to an irregular sparse model requiring some specialized techniques. Sparse GPT, for example, is a pruning technique that has been tested using the largest publicity accessible generative LLM model library, such as OPT 175 billion with the 175 billion parameters and Bloom 176. Researchers found that running sparse GPT in one-shot results with 50 to 60 sparsity reduction with negligible accuracy loss, measured either in terms of perplexity or zero-shot accuracy. And at the out of sparse GPT is an application of sparse regression on each layer of an LLM neural network. Sparse regression is a statistical method used for modeling relationship between variables in scenarios where the number of predictors, the independent variables, exceed the number of observation, or when the true underlying model is believed to be very sparse. Such as sparse regressions aim to select a subset of predictors that have the most significant impact and attribution on the outcome variable, the thing that we're trying to predict, while disregarding irrelevant predictors. This approach simplifies the model, enhances interpretability, of course, and help prevent overfitting compared to typical regression analysis, where all the predictors are being used. Semantic caching. That's one of my favorite topics. I think, caching is, again, a general term that is not specifically for LLMs. And caching is something that is really crucial, not only when you're deploying your own private LLM, but even when you are using a third-party vendor. Traditional caching from the software development ecosystem talk about exact matches, meaning there's a new income request, and we are trying to see if in the previous scene request, we already saw the exact same input, and if so, it's a it, and we will use the previous given answer as the output that should be delivered instead of actually trying to compute the answer for the new request that just came in. Now, this could dramatically, of course, reduce the cost or latency by going out to a third-party vendor or even for your own private LLM. But exact matches are really a big problem in the world of LLMs because, as you probably understand, the world of LLM is really all about loose interfaces and very natural way of asking questions, meaning it could very be that somebody or a lot of different users are actually asking the same question that require the same answer, but still every person that asked that in a different way or phrase it a bit differently or is using different phrases to express his question. But still we want to answer the same answer. So for that, we could do something that we call semantic caching, which is super useful in the world of LLM because, again, you won't see exact matches a lot. And LLMs already help us to do a lot of what semantic caching is all about, which is embeddings, meaning in the semantic caching process, what we will do is that for any new income request, we will find the relevant embedding that represent the question that we are facing. And then we just need to do some kind of a similarity search and to see if we already had similar enough questions in the past. Now, to do those similarity functions and retrievals, You could use vector DBs, which are really specialized for those type of searches, or even do an in-memory search. And if you did find something which is similar enough, again, some of the challenge here is to define what is similar enough. But if you do find, let's say, under a specific level of threshold, a similar enough question in the past, you could use the answer that was already given to that specific question. And again, as I said, avoid going out to ask again and use again OpenAI or your own private model. And in many cases, it could save something between 60 to 90% of the number of times that you really need to eat the underlying LLM model. So it is something relatively simple to implement, given that you are using LLM and given that you're already computing embeddings, but it is something that could dramatically and drastically remove the number of times that you eat the underlying LLM. Last thing that I want to mention is talking about putting LLMs in edge frameworks. So bringing LLMs to the edge is one of those things that I really believe could be one of the most interesting frontiers that the industry still need to tackle. If we think about it, the promise here is huge. Like, as we push more and more intensive computing to the edge, it could actually solve most of the biggest challenges that we are facing today. Whether it's latency, you don't, like when you are using LLMs in edge devices, you don't need to do unnecessary network operations. If it's the ability to work in offline environments, again, even though that everybody have internet and accessibility, in specific cases that you want high reliability and sometimes are quite remote, using LLM at the edge could bring you the benefit of working offline. And I think the most interesting point in doing LLM or generative AI type of work in edge is to enable federated approach to really to preserve raw data only in the edge and avoid to do some kind of a data sharing between different tenants, which is of course super important in specific verticals, especially those that are either highly regulated like healthcare or those that really need to put a lot of emphasis on data preserving and not sharing any data outside, like manufacturing. But I'm talking about that as one of the next frontiers because while it sounds like a magic and it sounds like something that sounds amazing, of course it comes with a lot of challenges that we are only starting to tackle, whether it's having strong enough edge devices that could really, have enough compute power or memory levels to host those models. And from the model perspective, we need the models to be small enough in order to be able to fit into those edge devices. But because both things are happening in parallel, and because, as we already talked today, and we know that there are stronger and stronger edge devices every day. And we just showed so many ways that you could shrink or be much more efficient when delivering an LLM model. I really believe that that's a very interesting frontier that will keep on moving forward. And as we will move forward, we'll see more and more appropriated use cases for edge devices. Last thing, I want to take like a step back for a second and just to compare ML versus LLM from some high-level technical considerations. And again, it's not like clear cut. LLM is not like something different from ML, just a sub part of what ML is all about. So while optimizing LLMs have proven promise as a solution for some use cases, it's worth noting that the sphere of influence and scope of use machine learning extend well beyond generative AI. The specific requirements of the application and task at hand, and both resource and task constraint play a significant role in determining which approach is more suitable for a given scenario. So let's try to evaluate, let me try to give you some high-level consideration when you are trying to evaluate between whether you should use traditional ML or to use LLM to solve the specific case. So let's talk about three main considerations. The first one, of course, the most obvious one, technical depth, cost / complexity. LLMs do offer a convenient means to handle the complexities and technical challenges of constructing machine learning and deep learning pipelines, but come with increased reliance on powerful GPUs and infrastructure, as we just talked about, which translate into direct cost for private LLM deployment or indirect cost when using managed services like closed source OpenAI models and third-party vendors. The other consideration is latency or richness trade-off, I would call it. So for tasks where delivering immediate result is crucial, like real-time predictions in milliseconds, a smaller, much more focused ML model, which is specialized for the case, may outperform even the most efficient closed-source LLMs. However, LLMs can significantly enhance the quality and depth of interactions, justifying a slight delay in response for contextually rich customer-facing solution or generative tasks that benefit greatly from the human feedback. So it is something that, of course, you sometimes could benefit from the richness or the accuracy level of LLMs, but if speed is really crucial and you must hit a 10 millisecond response, you sometimes should prefer something which is maybe at least a bit less accurate or generalized, but specialized and compact for this specific case. The last one is data leakage. In some scenarios where air-gapped solutions are imperative, cost analysis comparing a network of private LLMs deployed on premises, including hardware requirements with more traditional, simpler ML models may prompt developers to exercise cautions before exposing proprietary embeddings to closed source alternative. I think we talked about it, like the most state-of-the-art right now, LLM usage usually is being done using third-party vendors, and you just don't necessarily want or could use them in order to not expose any data outside of your net. So those are things I believe are the main considerations between when you should evaluate whether you should use like traditional ML approach or LLM approach. And with that, I will give it back to Moran to summarize this session. Mute, Moran.
Of course, someone had to do it at some point. Okay, so just to give a quick recap here. And I think, you know, we went through this a lot also on this session and also on the previous sessions, is there are limitations when we're looking at LLMs. And given those limitations, we don't always want to take a training route when we're going about how to overcome those limitations. So some of those things will be built around architectures, some of them will be algorithmic, some of them will be similar to the infrastructure things that Owen just covered now. And within that, we need to recognize what is the use case that we want to apply this to, and what are the different things that we can utilize for. But with that said, we really do need to take a TDD approach here. So experimentation is key here, because essentially we have a limited amount of things that we can play with compared to traditional ML models. So don't take this as something that is given. Take this as something that you need to constantly be tweaking or trying different syntaxes with, and different synonyms with, and to see how that will alter the outcomes that you have as you move forward. And with that said, with that twist that Owen gave us all at the end, is it never should be an either or discussion. So you should still be evaluating more traditional machine learning models, because sometimes simpler is going to be better for the specific use case. And nothing is also saying that you can't have more than one model applied to the use case and to the business application that you want to solve as well. So with that said, we do want to share, you know, all of the contact details, and I will also share the contact details in the follow-up. We have a few questions, but I'm going to give everyone a breather for a second before I put them on the spot to actually answer them. And it looks like for once we actually had good time management and we might actually finish on time. So let me go through the QA real quick. And if you have any more questions, just drop them in now and we'll answer them before we wrap up the session. So give me a second and let's look and see what we have here. So the first question we have is, how do you compute / measure uncertainty? So I think this one's probably going to be David.
Yeah, I can take that one. And I will share my screen really briefly. Just as a quick point of note, this harkens back to the question of how do we opt out with responses that may not be as confident? How do we handle the ego problem of LLMs, right? As mentioned, this concept of uncertainty is dependent on running the same prompt multiple times, right? So it just is a matter of the proportion of the answers associated with a given prompt. This is particular to questions that have concrete classifications or numerical responses. In the event that you want to go beyond that scope, I would point to token likelihood as an alternative, right? So effectively, regardless of how many times you are actually running your request, you can apply token likelihood, which is really just an embedding by embedding probability of how likely the LLM output actually was given the original request, right? So those type of analyses, I'd say either just through majority rule or threshold-based applications within uncertainty, or in the event that you don't want to go down the self-consistency route, token likelihood can apply either to self-consistency or to broader use cases. So I'd probably point to those two, but that's how you would do the calculations there. So.
Okay, so first of all, yes, I'm going to share also the presentation itself. So don't worry, you'll get all access to everything, all of anything that we showed here. So it will either have a link to the presentation. If we showed an external source, we'll try and give you the notebook as well. So don't worry about everything, you'll get it as well. There's two questions here. The first one, I'm clear on what we want, what the question is. So they're asking, can you give examples of different LLM applications that require subjective versus objective metrics? This one is clear, but I think there's an extension to that question here, which is what kind of use cases / problems / innovations have you seen when it comes to querying SCE data? So I'm not sure specifically to SCE data, but let's try and give it an answer. And I'm going to guess and assume that this is going to be Andrew.
I think SVC data I haven't worked with specifically, so maybe Oren or David could take that one.
Sure, but why don't you go ahead and answer the first one, and then someone else will pick up the ball, and hopefully we'll know how to give a more tangible response there.
Okay, sure. So objective versus subjective depends a lot on your use case, of course. So some examples of something that might require a subjective use case is whenever you have a generative use case, whenever you're needing to create text or create documents, those tend to use more subjective metrics, whereas objective metrics tend to be more analysis of documents. For example, if you have documents that have financial data, have documents that have more referenceable, queryable data, there you'll use more objective metrics typically.
Okay, cool. Does anyone have something to answer regarding the SCE data? If not, don't worry about it. We've already had questions in the past where the questions were new to us. We also include the questions and the answers in the follow-up. So sometimes we'll answer after the fact. So if someone knows on SCE data, go ahead and raise your voice. Otherwise, let's move over to the next one.
Yeah, I can speak on it high level. I think especially with respect to highly sensitive and highly confidential RAG systems, right, in which the knowledge base can't necessarily be exposed, right? Out of the box, it's worth noting that RAG configurations can be applied such that no general embeddings within GPT-4 or other alternatives are consulted, right? So you can make it very context exclusive, right? So those opt-outs to the web to a generally trained LLM like ChatGPT and the like don't necessarily need to be included within the RAG toolkit. It's also worth noting that within RAG, there are a lot of architectures out there that are really plug and play with private LLMs. That's something we've seen quite a bit with financial data, assuming that the queries are done internally. A lot of the URL extraction chains in LangChain, if in the event that you do have SEC documents on sam.gov or a particular government agency site in which a lot of this is publicly available, right? A lot of those web scrapers are built-in functionalities in generating a lot of these vector databases paired with something like ChromaDB and the like, right? So depending on both on the extraction side as well as retrieval, right, protecting against those confidentiality breaches, there are a lot of built-in functionalities that you can use, but more specifically, we'll follow up with more. So.
Okay, so I think we're for sure going to be able to do another 2, and anyone we didn't get to their questions, we'll answer it after the fact. So David, the next one is for you also. So the question is, if we're looking at legal agreements, how would we approach chunking, where typically, the chunks have references and context given subsections within the document. So how would you go about, pulling out a relevant answer when you wouldn't need to look at a specific paragraph, but you would need to understand the context of the paragraph within a specific subsection?
Yeah, so I'll answer this within the broader context of RAG systems, as well as some helpful alternatives that I think are really good emerging frontiers right now, right? So semantic chunking, short answer, would be your best bet here, because in the process of refactoring or reordering the sentences, the context within the entire parent document, in this case, across different legal agreements, pulling in very similar clauses and cases, etc., right? Those would all be considered together, and the LLM's interpretation of that parent document would get refactored to account for all of that context. I wouldn't necessarily restrict approaches to a RAG system in the case of legal documents, because you're probably getting close to something like a knowledge graph here, and there are a lot of LLM emerging frontiers around not only how to generate knowledge graphs through traditional autoencoders, but also through LLM enhancements, but also how to reference and actually query based on those structured entity relationships that you see in a knowledge graph. I have been familiar with a lot of knowledge graph implementations with LLMs in the legal space, and they've been really powerful. I would argue that they've not only rivaled, but exceeded the performance of even the best custom fine-tuned RAG system. So it's just an alternative to explore how you want to actually store the relationships in your data. Surely semantic chunking can do it, but in the event that a knowledge graph is working better for you, there are a lot of capabilities made available there too.
Cool. So we're going to do one last one. Half Olin and half David. So looking at semantic caching, how do you filter out storing incorrect responses for the LLM?
I can start. Short answer is you can decide on whether or not you want the user side, right? Or if you want it implicitly, right? So this comes with the rule-based implementation, or on the user side, accounting for positive feedback, right? So in the event that a response was in fact ruled to be positive, that could be implemented into the semantic cache. Obviously, you need to be mindful of compute restrictions here. You don't want your semantic cache to rack up a whole bunch of tokens. That may pose a threat to latency as well. So having that delicate balance, but certainly on the user side, that could be implemented as a way to distill and filter the bad input from the good input, right? You could also cross-reference against the semantic chunk as post-processing. So you could do something like a uniqueness evaluation and say, is this type of request fundamentally unique or fundamentally different from the requests made in the past that are currently stored in the semantic cache, right? So that could either be traditional similarity search, or you could have an LLM do that for you, just depending on what method works best for you. But in the event that it does pass a certain threshold, if you want to use cosine similarity in an alternative, right, you can implement it into the semantic cache directly after the fact internally too. So
I will just add to that that I think the fundamental challenge in detecting or in the question that was raised around caching wrong answers is being able to detect what's wrong or bad, to be able to evaluate that. Meaning, like, you could do that if they, like, based on further interaction with the user, like whether he expressed that the answer was good for him. Maybe it's based on some, explicit feedback like thumbs up, thumbs down, or maybe it's using some internal evaluation mechanism like getting answers from additional models and to see what is the majority of them are answering. Now, if you do invest more time or more functionality in evaluating those type of answers, so then if you do have an indication that this answer might be wrong, of course, you don't necessarily need to save that in your cache, or you could, in case that you did detected such a bad response from the user, you could decide to delete the existing answer from your caching. But I believe that the base challenge here is really to detect whether the answer is bad or not. And there's ways to assess that, but of course, it's not deterministic.
Okay, awesome. So we have more questions, but we've already hit our time. So anyone we didn't get to, we will, in the follow-up, answer your questions as well. And if anyone has a question that pops up into their mind after the fact, you all have my email. So feel free to send it over and we will do our best to answer it as well. So honestly, guys, thanks for sticking through. Like, it was a long hour and a half, and the majority of you are still here. And we will share everything in the next day or two, and see you all next time.